So on the periodic table, you might have noticed if you look at something like carbon, when you look at the mass number, you get 12.01. It's not a round number. The reason for that is because of the existence of several isotopes. Now, an isotope has the same number of protons as the regular atom, but a different number of neutrons. So if we look at carbon, there are three main isotopes of carbon. So there's carbon 12, carbon 13, and carbon 14. If we look at these symbols, it tells us a lot about what is in the atom, how the isotopes are different from each other. So the atomic mass up here, that tells you the number of protons plus neutrons. Okay, so in this case, the atomic number down here, so this is the atomic number, just call it the atomic number, that tells you the number of protons in the nucleus. So we've got the mass number, protons plus neutrons, and the atomic number gives us a number of protons. So from that we can figure out how many neutrons we have in the nucleus. So if we go over here, we have, so if we've got carbon 6, so we've got 6 protons, then we do 12, the atomic mass, minus the atomic number, and that tells us how many neutrons are in this atom. So here's a question. How many neutrons in carbon 13? How many neutrons in carbon 14? So for carbon 13, we've got 6 protons again. And for carbon 13, we've got 13, so the mass number minus the atomic number 6, we've got 7 neutrons. So this is heavier. So carbon 13 is heavier than carbon 12. If we go down here, carbon 14, 6 protons, and again, 14 minus 6, that means we've got 8 neutrons. Now, why is this important? Most carbon that you see, if you burn a piece of wood and you look at the charcoal, most of the carbon atoms, if you could zoom in on them deep enough, you'd see would be this carbon 12. That's the most common form of carbon. There are small amounts of carbon 13 and carbon 14 present as well. They react exactly the same way as carbon does because they have the same number of electrons as carbon. So when we're doing chemical reactions, we're looking at electrons. But they're slightly heavier, and they also have some other different properties. Carbon 14 down here is radioactive. Its half-life is about 5,730 years. I'll talk about why that's important a bit later on. Now, the way in which I've shown these symbols, where I've got the element symbol here, the atomic number down the bottom, and the mass number at the top, that's a very common way of doing it. So we have X, Z, and A. X is the symbol for the elements. Z is the atomic number. And A is the mass number. Okay, so that's a very common way of showing these isotope symbols. So let's go into a bit of detail about the isotopes of carbon. Like I said, most of the carbon atoms around you, on the table that you're leaning on probably now, most of those are this carbon 12, so 6 protons and 6 neutrons in the nucleus. A very small proportion of the carbon atoms near you are carbon 13, so 7 neutrons, 6 protons, and then a very, very small proportion are carbon 14. Now, these small proportions here mean that on average, a carbon atom has a mass, relative atomic mass of 12.01. The relative atomic mass down here, or atomic mass that we talk about, this is the average mass of an atom compared to carbon 12. So carbon 12 is this one, so that has a mass of 12, we call that 12. But carbon's overall average mass is 12.01 because we have this small proportion of these heavier naturally occurring isotopes of carbon. So if you pick carbon up, if you had 1 mole of carbon, we'll talk about moles a bit later on, 1 mole of carbon would weigh 12.01 grams, not 12.00 because we have this small proportion of carbon that weighs a bit more. We're going to talk about carbon 14 briefly. This is very handy in archaeology. Like I said, it has a half-life of 5,730 years. While you're alive, you're taking in carbon. So you're eating food that contains carbon. That carbon gets distributed around your body in things like the fats and the sugars and proteins in your body. And when you die, you stop taking in that carbon 14. And this carbon 14, because it's radioactive, it starts breaking down. So it breaks down into other elements that aren't as radioactive. So over time, the amount of carbon-14 in your body decreases, and after 5,730 years, you have half the amount of carbon-14 in your body than you would today if you're alive. So if I died, my body was buried, 5,730 years later, I would have half the amount of carbon-14 in my body than I do today. So archaeologists use this to date how long it's been since things have died, because when things die, they stop taking in carbon-14. So the amount of carbon-14 present decreases over time, and what they analyse is the amount of carbon-14 compared to carbon-12 in the organism's body, or the leftover remains of the organism, to figure out how long it's been since it's died. This can be used to date pretty much anything organic to around about 10,000 years, maybe 20,000 years at a stretch.